Last time we talked about towers of field extensions, and we talked about the case when if we have a field extension L over K and alpha is an element of L, then we considered the subfield K adjoin alpha, which is the smallest subfield of L that contains both K and alpha. So K of alpha was the subfield of L obtained from K by adjoining alpha. This time we will talk about what it means to adjoin alpha to K abstractly. That is when alpha is not an element of a given field extension. And the construction that we will be working with is as follows. Construction of adjoining a root of an irreducible polynomial. So let's take K, a field, and let F be an irreducible element, irreducible monic polynomial. Of some positive degree. Then we take the quotient ring, which I denote by L, the quotient ring of the ring of polynomials over K, quotient out by f of x. What we can observe is that this construction comes with a homomorphism, an injective homomorphism from K into K adjoin x, mod out by the ideal generated by F. Such that the equivalence class of x, which I will denote by alpha, is a root of the polynomial f of x. So f applied to alpha is equal to 0 in L. And further, we can observe that L is a field. So f is an irreducible polynomial So K adjoint X is a principal ideal domain. So the ideal generated by an irreducible element is maximal. So this is a maximal ideal. And therefore its quotient is a field. Therefore L, which is the quotient of K adjoint X by this maximal ideal, is a field. And as a conclusion, we get that L is now a field extension of K, which is obtained from K by adjoining a root of F with alpha in L. So we know that we can choose an element alpha in L. It is some root of F of X, which can be viewed as a polynomial with coefficients in L. And there are some other observations that we can make immediately. So first, L, which was defined as this quotient of the ring of polynomials by a monic polynomial, is isomorphic as a K vector space to K taken with itself degree F times as K vector spaces. So L over K is a finite field extension whose degree is the degree of F. And alpha is an algebraic element over K with minimal polynomial F. With minimal polynomial F, because alpha is a root of F over L, but F is irreducible over K. And these are two characteristic properties of being a minimal polynomial. Also with the assumption that the polynomial is monic, so the leading coefficient is equal to 1. Let's consider some examples. Example number 1. I can consider the polynomial f of x to be equal to x squared plus 1, and I can view it as a polynomial with real coefficients. Then by adjoining a root of f, I get a field which is isomorphic to C. So I get the field R adjoint X mod out by f of X, and this is isomorphic to C. And we have that I, an element of C, is a root of this polynomial, so we have that f of x is equal to x minus I times x plus I over C. So this polynomial splits into linear factors. The second example, which you are working out in your homework, I can consider the polynomial f of x equal to x cubed minus 2, a polynomial in Q adjoint x. It is irreducible over Q. And so we get a field extension Q adjoin x mod out by f of x. If I say that alpha in L is a root of f of x, then I can split f of x into the product, into the following product of two irreducible factors. X minus alpha times x squared plus alpha x plus alpha squared. So the second factor is irreducible. And so we see that in this case, f of x in this field extension does not split into linear factors. And the last example, I consider the base field K will be the field with two elements, and I take f of x to be equal to x cubed plus x plus 1. So f of x is an element of f2 adjoin x, and it is an irreducible monic polynomial. Then, applying the same construction, I get the field extension L, f2 adjoin x mod out by the ideal generated by f. The degree of f is 3, so I have that L is an extension of degree 3 over f2. So we have a three-dimensional vector space over f2, and therefore it has 8 elements, and I denote this field by f sub 8 because it has 8 elements. And let alpha in f8 be a root of f. Then I claim that this polynomial f of x splits completely over f8. Which means that I can split it into linear factors. So f of x is equal to f plus alpha. So I usually write x minus alpha, but over f2 plus 1 is equal to minus 1. So I can just write all pluses and not care about signs. So f of x is equal to x plus alpha times x plus alpha squared times x plus alpha squared as an element of f8 adjoin x. And so a formal definition of this notion splits completely is the following. I say that a polynomial f of x with coefficients in k splits completely over k if it factors into linear factors over k. So for example, in number 1 and number 3 here, our polynomial f of x splits completely over the field extension L. So in the first example, we have a product of 2 linear factors, and in the third example, we have a product of 3 linear factors. And in number 2, f of x doesn't split completely over either k or L. So we know that adjoining one root of an irreducible polynomial can lead to a situation where it would split completely over a field extension, split into linear factors, but it may not. It may also not give this situation. And in general, we can prove the proposition that for any fixed polynomial, we can find a field extension where this polynomial splits completely. So if k is a field and f of x in k adjoin x is a monic polynomial of positive degree, then I claim that there exists a field extension L of k such that f splits completely over L. The proof works by induction on the degree of f. Induct on D, where D is the degree of f. The case where D is equal to 1 is trivial because we can take L is equal to k, and then f of x is a linear polynomial, so it is a product of one linear polynomial. So in this case it holds. Now assume that we know proposition for a degree d for all degree d polynomials, and we want to assume that the degree of f is equal to d plus 1, and prove that we can find a field where f splits completely. Case number 1 is when f of x has a root, say alpha in k. Then there exists a polynomial g in k adjoin x such that f of x is equal to x minus alpha times g of x. So in this case, the degree of g of x is equal to d because the degree of f is d plus 1. And so we can find L such that g, L an extension of k such that g splits completely over L. but then the same L works for F. And this is because F is a product of a linear factor times some more linear factors that we split over L. So the case that we are left with is when f of x doesn't have a root. Then we can take any irreducible factor of f which means that f of x is equal to g of x times some other polynomial, and g is irreducible. Then we can denote by k prime the field extension which is obtained from k by adjoining a root of g, k of x mod out by g. And this is a field, and this is a field extension of k. Then f of x has a root in k prime, because g has a root in k prime, and g is a factor of f. So we can apply the result of case 1 to f viewed as a polynomial with coefficients in k prime. And then we get a field extension L over k prime, where f splits completely over L, and k prime is an extension of k, so L is an extension of k, where f splits completely. And this proposition that we have just proved motivates the following definition. If k is some field and f is a polynomial in x of degree greater than 0, then we say that a splitting field for f over k is a field extension of k, is such a field extension L, so that f splits completely over L, and satisfies a certain minimality property. So if we say that f of x is a product of x minus alpha 1 through x minus alpha n, probably multiplied by a non-zero constant, everything here, where alpha i's are roots of f in L. Then the minimality property that we want to assume for L is that L is obtained from K by adjoining all the roots of F and nothing else. So L is equal to, so L is the smallest subfield that contains K and all the roots alpha 1 through alpha n. And we can prove some facts about splitting fields. So lemma number 1, if we have a chain of field extensions, F and K in L are fields, and F is a polynomial in F adjoin F, F adjoin X, then if L is a splitting field for F over F, for the polynomial F over the field F, then L is also a splitting field for the same polynomial over the larger field K. The proof is rather tautological. So we know that F splits completely into linear factors, and we know that L is equal to F adjoin alpha 1 through alpha n. So if we add some more elements to K, or to F, so we consider K adjoin alpha 1 through alpha n, then it will still be the minimal subfield that contains F and all alpha 1 through alpha n. Lemma number 2 says that every polynomial F in K adjoin X of positive degree has a splitting field. And the essential part of the proof was done when we proved this proposition. So proof of lemma 2 is that we pick L where F splits completely, over L. Such an L exists because of this proposition that we have just proved. Then, if we choose roots, all the roots of F, then L prime, which is the smallest field containing K and all the roots, it will be a subfield of L, and it will be the splitting field of F. So we have that F splits completely over L prime, and also this field L prime satisfies the property that it is obtained from K by adjoining all the roots of F. lemma number 3. A splitting field is a finite extension and moreover every finite extension is contained in some splitting field. Polynomial f over k. So proof of lemma number 3. So we recall from the previous lecture that we had corollary number 4, which said that a field extension is finite if and only if it is obtained from the base field, in our case it is K, by adjoining finitely many algebraic elements. So in the forward direction, if we have a splitting field over K, from the definition we know that a splitting field is obtained from K by adjoining the roots alpha 1 through alpha n of some polynomial, and since they are roots, all these elements are algebraic. So by corollary 4, it is a finite extension. In the other direction, assume that we have a finite extension, L over K, finite field extension. So again, by corollary 4, L is equal to K adjoin alpha 1 through alpha n for some algebraic elements alpha I in L. Then we can consider the product of all the minimal polynomials. So f of x is defined to be the product is defined as the product of the minimal polynomials alpha 1 over k times dot dot dots alpha n over k of x. So this is a polynomial with coefficients in k. And so we can adjoin roots of f to L. And so we get that a splitting field L prime for f over K. This field L prime will contain L. And so we proved that our finite field extension is contained in a splitting field for a certain polynomial f, which we chose to be the product of all minimal polynomials. defined a splitting field of a certain polynomial, but vaguely we can say that it is not important which polynomial we choose as long as it has a root in the splitting field. So the vague idea is that it is not important which polynomial we choose to define a splitting field L over K. As long as F is irreducible over K and has a root in L. Then adjoining all the roots of F will give us a field extension which is isomorphic to L. More precisely, we can state the splitting theorem, which I'm not going to prove now. So we have a field K. We have a polynomial f of positive degree, and we have L over K, which is a splitting field for f over K. And now take any irreducible polynomial. If G in K adjoin X is any irreducible polynomial, and has a root in L, then G splits completely over L. And so now we have that a splitting field allows certain polynomials reducible polynomials over K to be split completely. But not all irreducible polynomials will have a root in L. However, there exists a construction which allows us to choose a larger field, a field extension of K, that adjoins all the roots of all the polynomials. And for this, after we do this, we obtain a so-called algebraically closed field. So by definition, we say that field L is algebraically closed, if every polynomial with coefficients in L has a root in L. For example, C, the field of complex numbers is algebraically closed. And there is a theorem that says that if K is any field, then there exists a field extension L over K such that L is algebraically closed. And then the smallest such K, such L, is called the algebraic closure of K. And all algebraic closures of a fixed field are isomorphic. The proof uses Zorn's lemma, which is one of the axioms in mathematics, and some people don't choose to believe in it. However, usually we assume that algebraic closures do exist.